All right, hey guys. Hey, I just wanted to go through this free response question dealing with thermodynamics. So this is on page um, 17 of our review packet. Just kind of go through the thought process that I had as I was working through it. Obviously, you have the answer key in the back and scoring guide, so use that to help. But here's kind of how I thought through the process. So first off, it gives us a sample of gas, three samples, X, Y, and Z, and to me, they're all the same gas, right? So basically what I'm looking at is I'm looking at their temperatures. Remember when we looked at this, that the temperature deals with the speed in terms of its kinetic energy. Temperature measures average kinetic energy, so the faster something is moving, the higher its temperature is going to be, right? But also remember that there's going to be a range of speeds. It's just the average kinetic energy. So there's going to be some that are moving faster, there's going to be some that are moving slower. So the average kinetic energy. So temperature X is Tx, temperature of sample Y is lower than that of X. So the average kinetic energy then should be lower. So it should have a lower average speed because all three gases have the same amount. This area under the curve for all of them should be the same, right? So that's why you're going to see X have a greater speed. It has a higher temperature, so it should have a higher average kinetic energy, but the curve should be lower. Very fitting for our current situation, right? Flatten that curve as the temperature goes up. Sample Z has the lowest temperature, and so what we're going to see is its average kinetic energy should have the lowest speed. However, it's going to have more particles within that speed, so that's why we have a higher curve there. Okay. Second part of the problem then, it looks at X, Y, and Z. X is the highest temperature, Y is the second highest, and then Z is the lowest. They're going to come together, they're going to be in contact, and it wants you to talk about the average kinetic energy of the molecules until they reach equilibrium. And basically what it says is the samples eventually reach equilibrium with a final temperature which is greater than Ty. So if we look up here, it's going to be somewhere between the initial temperature of X and the initial temperature of Y. Okay, so here's how I kind of explain things. So basically, temperature X is greater than temperature Z. That means that X will then transfer thermal energy into Z. This will cause the average kinetic energy of X to decrease until basically all three of them are in equilibrium. Now, depending upon the rate of transfer, it could actually drop lower than T final, right? So it could reverse back as well. It just depends. More than likely, though, because X is the highest, it's only going to decrease the entire time. Okay. For Y, and if you look at the scoring guidelines, right, it wants you to be able to show that this process can reverse. It doesn't only have to go one way. It can stop and it can go back the other way. So it's kind of why they're organized the way that they are. Here's what I said for Y. Ty is greater than Tz. That means that thermal energy will be transferred into Z from Y and lower its kinetic energy. Since Z then becomes greater than Ty, because Z is not only has thermal energy being transferred from Y, but also from X. So Z is increasing its thermal energy pretty quickly at the very beginning. Basically, what's going to happen is I predict that Z then will start transferring thermal energy back into Y because what we know is we know that the temperature final has to be greater than the initial temperature of Y. So Y will become a hotter substance. It's just going to take time because it's going to have to dump energy into Z and then wait for Z to dump energy back into it. So that means that the average kinetic energy will also increase again, showing that process can happen both ways. Z receives thermal energy from X and Y. This increases its average kinetic energy. It then transfers back into Y. The average kinetic energy could decrease depending upon if it reaches a temperature greater than Tf prior to equilibrium, or T final, excuse me. So if it actually gets hotter than what it will be at the very end, it can decrease as well. So in the scoring guideline, they give you leeway in terms of how you go about explaining it. Okay. For C, entropy, this is the most I've ever seen entropy talked about on an AP2 exam, but it is something they want us to know. So indicate what the entropy does in sample X. X actually decreases in terms of its entropy. Because the final temperature is less than the initial temperature, there's less spread out in terms of its average kinetic energy, so it's actually become more organized. It's one way that I think about it. Check the score guideline for kind of their interpretation of it. For the 3-sample system, basically what we've talked about is that entropy always is going to increase, right? Particles become more spread out. While initially they were segregated in these 3 different substances, now they are able to move throughout, and so you don't just have nice organized patterns of the 3 different temperatures, but now they're all spread out. So particles have spread out all over. The natural process of a system is always to increase its entropy. Okay, so hopefully that helps. Just a quick explanation of that problem. Shoot me a question on our discussion board if you have any. Otherwise, look for more free response questions coming up.